Minya, Helena, I'm Virtual Neko, Nekomiya Sebastian, and welcome to Sneko's 3D devlog series where I'm making a 3D engine from scratch without using any graphics libraries, doing it all by hand. Today I got an awesome new addition. As you can see here, we got this lighting test scene. Let's check it out. So we have this awesome sphere here, this globe, and then you can like check it out, zoom around, and then you're like, oh, but it's the lighting. You could have just done this like by hand, like fair enough, right? But then we can rotate the lighting, so it's actually, whee, it's actually happening, yeah! You can rotate around this way, and anyway, I thought that was very cool. This is the lighting. This unlocks a ton of possibilities for us in the future, in addition with the other additions we've made, so let's check it out. So, lighting is actually pretty, well, not simple, but easier than the previous things we did. So what did we add here? We added a center, and this is different from the position in the transform, the transneko, sorry. It's the average of all the points, so it's like a true center rather than just an offset. And then we got a list of cached normals, list of cached colors, talk about that in a second, and then this invalidate lighting can only be in here because the transform doesn't have any lighting. Transneko, sorry. And then this is the same. We added this. So how does lighting work? We have a light, or let me make a diagram for this. Hold on. We have a light. Yay. And it's shooting out rays in every direction. And let's say our object is here. I don't know what kind of object this is supposed to be. Oh dear. This is our object here. Supposedly a cube. And the light will hit this cube at this angle right here, right? And we know from the normals that the face angle is like this. And so this face is like going to be completely lit. So the way we do this is with dot product. So the way it works is it's basically how rotated two vectors are towards each other. So let's say you have sunlight going like this way, like just hitting this top face, but the top normal is like this. So these are like perpendicular to each other. This dot product will return 0 because they're exactly, or like roughly perpendicular. And then let's take this back face here. The sun is not going to hit it, but it will in this kind of math. They're facing the same direction, so it's going to return a 1, as in like they're exactly the same direction. That's how dot product works. And the way you do it is actually really simple. We have two vectors, A, B, C, dot. So how you do dot? D, E, F. Equals, it's A times D plus B times E plus C times F. You just do this plus this plus this. Super simple, super performant. It's amazing. And so, knowing this math from the dot product and the light direction and the face direction, we can translate this into code. So we get the forward direction of the light. This is just done by applying a rotation matrix. Oh, let me show what I'm doing real quick, show my work. This is done by applying the rotation matrix of the object. And the light object, here it is right here, is just a transneko. It has a couple colors, light and dark, to interpolate between. And of course the direction that it's looking at. And then, so yeah, the rotation matrix is applied to the forward vector. So it looks forward and the object's rotation, that forward is now its forward. Does that make sense? So yeah, we rotate by the transform and then by the camera. We have to do it in that order for some reason, just like above. And so now what we have is a transformed angle, like in what we're seeing on screen space. Like when we look on screen here, we see this is like in front of us, even though in world space, the camera's like here and this thing's like over here. To us, it looks like it's in front of us. So we're getting that angle all in this like normalized sort of space, or transformed space, I guess, rather. So this, the reason we do this is because we use the faces, which are also in that space. So everything's in the same like space. That's like really important in this 3D situation, I've learned. We recalculate the normals if we need to, and how we do this is we just do the difference. These aren't true normals. This is just the difference between the center of the object I described above to the face. So just like if it's a sphere, right, it's just looking out in every direction. If it's a cube, same thing. You get the idea. right? And so we need the normals for the lighting because like I showed in the picture, these little red lines here, these and like these are the normals. That's what we need. These yellow lines from the sun, this is just the rotation direction. It doesn't actually point things here. I mean, I guess we could do that if we had a point light. Maybe that's a future update, I don't know. But yeah, so we calculate the dot product of the lighting forward direction to the normal of the current face, where we're looping over all the faces here. And then we call this light color function, and we pass in the dot product result, the base color, and then the cached colors, which are going to set. So if you look in here, here it is. So based on the dot product, if it's less than 0, that means they're facing away from each other. That means it's going to be darker, right? If we look at our awesome diagram here, this face is going to be darker, and this face you can't see because it's away, but like this face is going to be lighter. Or it's a gray, and then this one's just going to be pure white because it's like directly baked in sunlight, this one here, right? And then, yeah, oh, so this is the color. Let me show the color real quick because this will help describe things. Pretty simple, net color. So we have RGB, red, green, and blue. And before what we were using, let me open up one of our previous Minecraft scene. Here we go. Before we were using these hex codes, which is like a system of like just typing out easy. Like if you use Krita or like whatever Photoshop, you can select a color, copy paste the code is like super easy. But the problem is these are hard to like interpolate, which is what we need for colors, right? We need to interpolate between the base color and like a light or dark version of it. So it's just a helper function to convert from a hex code to a regular RGB. And that happens here. There's actually like a function for it. It just gives you the value of that space. Anyway, so now that we have the RGB, we can lerp it. And what this does, instead of creating a new object and like setting it and creating junk garbage memory, it just sets the values. So this is like a little more efficient, I think. And then to get the actual color, you just do this RGB and then R, G, B. You got the deal. This is another way to draw colors in HTML or JavaScript only. I think it's both, probably, surely. Anyway, so and then that's the light that we're or no, this is the lit colors at this face index. Remember, the colors and the faces are the same, like what is that, list length? There's not a color for each point, there's a color for each face, so it's different than traditional 3D, I believe. And yeah, these are the cached colors, which is important because you don't want to light the color and then have to, like, you know, recalculate what it was before, and annoying. Anyway, the other thing we did here is a function to check whether the face is facing the camera, which we didn't have before. This is back face culling, I believe. And so normally what you do is you get the triangle and you do like cross product and you can find the normal, but we calculated the normals earlier anyway. And so here what we can do is just get the dot product result of this, what is this? The center to the base, or the normal. So the reason you use center here and not forward is because this, these normals, the faces, these are already transformed into screen space. So if you look at the screen here, this is in front of us, right? Even though in the world, like, the camera is here and it's over here, it looks like it's in front of us. And so instead of using forward, which is a direction that points like this, from right to left on screen or something like that, it's pointing from us, the viewer, out to this. So if you think about it that way, we're at 0, 0 looking at it. The position of the object is essentially, I mean, it's a position, right? But it's also a direction vector from 0, 0 to itself, if you think about it that way. So it's a little confusing, but yeah, so the get center is actually just an offset of itself to that position. So we dot that with the normal of that face, and that tells us how much it's looking in the same direction as the camera. And we do the same less than 0 thing, and it returns whether it's looking at the camera. And so if you look at this scene, actually, you'll notice even if we zoom in a bunch, we can see all the faces of the model, right? Look what happens if we go inside it. We see nothing. Even if we're moving the mouse, we're clicking and dragging around, nothing. But then we zoom out just a little bit and we see it again. What's happening is all the faces on the other side aren't getting drawn because that's the backwards, this is the inside of the model. You shouldn't be seeing this ever. So that's why they're disappearing. That's this code in action. Now the last thing I did want to show off is how we generate this cool globe, because I think it's really cool. Here we go. And this may need a chart, we'll see. So we get the two poles. Yeah, we'll do some drawing. Okay. So we get the two poles of the object right here and here. That's like, you know, top and bottom, north and south, whatever you want to think. And then we do a bunch of math for like angles and stuff. And basically what this is doing is we want to say we have a globe that looks like this. Let's see, it has two like layers. So if this is longitude, this is latitude, this is 3 latitude, 2 longitude. Move these over here. And so how does this work? We generate a rotation matrix based on the angle from each point in either latitude or longitude to each other. So like here or here. And so what this angle is going to be is this here or this to here. That's what those angles are. And then we get a rotation matrix. So for the latitude, that's going to be around the y. So that's rotation like looking left and right. Here, this one. Looking left and right, so it's going to be this angle for the latitude matrix. And so we'll start at the first point, this one. You'll go here, and then here, and then back. I guess it would make more sense to have a point back there, but you get the deal. And similarly, it's going to go here. Each step is going this much, and again. And then longitude is the same thing. It's just rotating around z, which if you think about it, oh gosh dang thing here, this. The z, if you think about it, it's like tilt, like it tilts your head like this. Y is like looking left and right. Z is tilt. And so that's going to be tilting around this axis here. So it's going to be here and here and here. And so that will draw our longitude lines. I hope I'm getting those correct because I always confuse them in school, but that's the general, and of course these will connect, but we won't see that. It's going to be like this thing right behind it. Yeah. So, yeah, we get each of those points and, oh gosh dang, Alt tab, okay. And then they go out a distance of radius, so they're all radius distance away from each other. We apply the rotation matrix and then put them in the list. Now this next part was just trial and error. So this is generating the faces. And so the way we generate is we're gonna have these like, it's gonna be like this. That's how they're going to be looped. It starts like 0, 1 for the poles, and then 2, 3, 4, 5, 6, 7. It goes that rotating, spiraling order. So it's easy to get the bottom and connect it. It's easy to get at the top. Oh gosh dang, Alt tab. It's easy to get at the bottom and connect it. Same for the top, because it's a single, you're just connecting to the pole. But the interesting part is these in-between faces where, let's get rid of that. So the first lines we're doing, the first polygons are these, right? Connecting to the top and like that, connecting to the bottom in whatever order we do it. The interesting part is these middle polygons here. How do we connect those? And the thing just by like trial and error and looking at what the array looks like, is the lines look like this: 0, 1, 2. Or wait, let's do it from the bottom because I think that's how it works. 0, 1, 2, 3, 4, 5. So the way they work is they actually spiral like this, but for the next row they go back one. So you'd think it'd be 0, 1, 2, 0, 1, 2. It'd be 3, 4, 5. It'd be the same one, but it's, for some reason it's offset back by one. I can't explain why this happens mathematically. I'm very sorry. Not my math. Math is not my forte or something, but anyway, it goes back one. It always goes back one. And so we can use this to math out which one is our previous, our current, our above us one, previous, and then next. That will draw us our square or our polygon. And we do that for all the faces, for all the rows, and that's how this works. And then we just do random colors, or I made it so you can set a color. Oh gosh dang, hey, go back to the thing. And then here, I made it so you can set a single color and everything's to that, or it just does a random color otherwise. And the way this works in the scene is we have the disco toggle mode. So I think I didn't show this yet. But the way this works is you press spacebar, and there, hooray! It gets all these random colors, and they're still lit. Like you see, it's kind of harder to tell since they're random. Not the same like brightness to start with. But yeah, disco mode. And so that's how that works. Is there anything interesting in here? This is just all the same. We've seen all this before. Streamline the tutorial process. Yeah, that's lighting. Awesome. Thanks for checking it out. I hope this was, I don't know, informative or interesting or silly. I don't know, something. That's how you implement lighting in your 3D engine from scratch. For anybody that wanted to do that. And this unlocks a ton of possibilities for us. Just normals add so much. Like we can now, I don't know, light objects. We can probably do cool stuff with them. Anyway, I think this will be really cool. And especially for like the project I talked about where you could add points and like create your own custom 3D models in this engine. The reason I was holding off on it is because I wanted lighting first, because I wanted them to be like the same color, or at least that to be an option, not just random colors. But if the same color, it looks like, you know, you can't even see the shape. It just looks like nothing without the light. So the fact that we have the light now, we can now do that. We can now make like sort of even like semi-game style levels after that. Like this is the direction of progress and it's awesome. So anyway, thanks for checking out and I'll see you in the next one. Bye.